Math.Santhi from Department of Mathematics and Statistics, Bhavan Vivekananda College of Science, Humanities and Commerce. I am here with lesson 11 from linear algebra on vector spaces. In this lesson, we will go through few more problems on linearly independent and linearly dependent sets only. So let us see the first one. Find the value of h for which the following vectors are linearly dependent. So here you are given three vectors, but here the thing is you have a vector. In this there is an unknown value h. So now you have to find out for what value of h these three vectors will be linearly dependent. So we will work this problem as LILD problem. So how we were solving LILD problem? We had two methods. First one is determinant of matrix method. Second one is echelon form. And we will see here these three vectors are given, three column vectors, and how many rows? Three rows. So three columns and three rows, a 3 by 3 matrix, square matrix you will get. So let us take, let A is equal to the matrix 2 minus 2 4, 4 minus 6 7, minus 2 2 h, and then since it is a 3 by 3 matrix, we will use determinant method. Method 1, that is determinant method will be used. So what is det A? Det A is equal to det 2 4 minus 2 minus 2 minus 6 2 4 7 h, which is equal to, so expanding on the first row, so I have 2 into minus 6h minus 14, then minus 4 into minus 2h minus 8, and then minus 2 into minus 14 plus 24. So this, if I simplify this, we will get the value. So this is minus 12h minus 28 plus 8h plus 32 plus 28 minus 48, on solving which we will get minus 4h minus 16. Now what is it given? These vectors are to be linearly dependent. So we have here, if the vectors are LD, then det A is equal to 0. That implies, what is det A value here? We have minus 4h minus 16 is equal to 0, which implies h is equal to minus 4. So what do we have here? For h is equal to minus 4, the vectors are linearly dependent. Now let us do another problem. Here we have, for what value of h the following vectors are linearly dependent. So here you have vectors, three vectors v1, v2, v3, where in v3 you have an unknown value h. Now you have to determine for what value of h the vectors are linearly dependent. So I will do this problem using both the methods. One is determinant method, another one is echelon form method. I can use determinant method because I have three vectors with the three rows, so I will get a 3 by 3 matrix if I take only A, so that I can do it by determinant method. So otherwise, if I don't get it, I cannot do by determinant method. So I am using, first one is the determinant method. So in determinant method, we will take A is equal to 1 minus 3 minus 5 minus 3 9 15, and then 2 minus 5 and h, then it is a 3 by 3 matrix. Then what will be determinant of A? It is 1 into 9h plus 75 minus of minus 3 into minus 3h minus 25 plus 2 into minus 45 plus 45. So this is equal to, implies that A is equal to, so this is 9h plus 75 minus 9h minus 75 plus 2 into 0 is equal to 0. Implies you are getting that A is equal to 0. Whatever the value h may be, that is whatever h may be. Then what do you mean by that? So this is LD. These vectors are linearly dependent for whatever the value h may be. Therefore, they are LD for all values of h. But now we'll do the same problem with the echelon form method. So I will use now echelon form method, because when you don't get a square matrix with the given vectors, you must use echelon form only. So I will give here echelon form method also, so you can apply according to the requirement. For echelon form, what do you do? Directly I am taking augmented matrix. I'm not writing now the equations, how equations are converting into augmented matrix. How do you write directly augmented matrix? See the vectors. What are the vectors given? Write them as columns. 1, minus 3, minus 5, and then minus 3, 9, and 15, 2, minus 5, and h. You should add here 0, 0, 0, because you will get a homogeneous system. As you have seen in the previous problem, the last column will be 0, 0, 0 in LILD problems. Now this we have to reduce it to echelon form. So first you mark the pivot position. This is 1. Using this one you have to make R2 and R3 first elements zeros. So what do you do here is, for R2 you will apply R2 plus 3 times R1. Multiply R1 with 3 and add it to this. So minus 3 plus 3 times 1 will be 0. So I'll use that. Then let me see here. What is it transformed to the matrix? 1 minus 3, 2, 0. And then this is 0. And then next 9. So this is 9 plus 3 into minus 3. That is also 0 here. And the next one, minus 5 plus 3 into 2 is 1. So this is 1. And now for the row 3. Row 3 I have minus 5 here, and I have to using this one I have to make it 0. So let us see how to do that. So for row 3 I have minus 5 here and I have 1 here. So what do you do? This multiply with 1. So what is that? You have to use R3 plus 5 times R1. So R3 plus 5 times R1. So you got here 0, because already that you have checked it with this 0. And then 15 plus 5 into minus 3. So this is also getting 0. Next you have here h. You have to be careful with this unknown value. So what do I have here? H plus 5 into 2. So that is 10 plus h. So I have here 10 plus h, and this is also, this is here 0 because nothing to check here. The previous elements are zeros. So now let us mark the pivot entries. Where is the pivot position here? Then can I mark any pivot element in the third row? No, because in this column already there is one pivot element. You cannot mark this as pivot. But now we have to make this as 0. Now let us make this one as 0. How do we make 0? For R3 I have to change. What do I have to do? So 10 plus h I have, and here I have 1. So how can this be 0? So 10 plus h and this 1 multiply with the 10 plus h. So that is, let me write it clearly. You have 10 plus h here and you have 1 here. So this one. So you just take this and multiply, then subtract it with 10 plus h into 1. That is R3 minus 10 plus h into R2. So what am I going to do? R3 minus 10 plus h into R2. So this will give me the matrix 1 minus 3 2 and then 0 0 1 0 and then 0 0 0 0, and here the pivot entries are 1 and this one only 1. Now let us see which are pivot columns, which are not pivot columns. C1, C2, C3. So C1 is a pivot column, C2 is not a pivot column, C3 is a pivot column. So what are pivot columns for me? That is C1, C3. Implies variables, two variables, C1, C3 variables are basic variables. Then, and therefore C2 is a free variable. What if there is a free variable? It has infinite solutions. Whenever it has infinite solution, the vectors will be linearly dependent. Implies the vectors are LD. Here there is no, irrespective of whatever the value of h, they are linearly dependent. The vectors of are LD for every value of h, because they are not depending on h. Here are few more problems for you to practice. The same model, for what value of h the following are linearly dependent. So same way you are given three vectors here. So you can use any of the method either by determinant or echelon form, and you have to determine for what value of h these three are linearly dependent. The same way second bit also three vectors are given, and for what value of this h these three vectors are linearly dependent, you have to determine that. Now let us see some basic points regarding LILD sets containing one or two vectors. Previous to this, we have worked out some problems where you had more than two vectors, either 3 or 4 or 5. So the methods what we discussed and we solved the problems, they were when you have vectors which are more than 2 in number. Suppose if you have either one or two vectors, you need not work out much. You can just decide by observing the given vectors. Regarding that, let us go through these basic points. The first one is a single zero vector is always linearly dependent. That means if I consider a set which has set containing 0, that means this set has only 0 vector, then what can it be? It is linearly dependent. Why? Because only one vector is there, so take one scalar a. So write linear combination a into 0 is equal to 0. Then this will be true, this equation will be true if you take a 0 value or even if you take a non-zero value also. That is, this is 0 for any scalar a, that is whether a is not equal to 0 or a is equal to 0. What do you mean by that? This vector equation has a zero solution and also a non-zero solution. Whenever it has a non-zero solution, whenever you get scalars, non-zero scalars, then that set of vectors will be linearly dependent. So if you have a singleton set, that is a set having a single vector, that to zero vector, then that set is always linearly dependent. Then let us see the second one. A single non-zero vector is always linearly independent. So now we will consider a set containing u, only one vector, where u is a non-zero vector. Previous to this you have taken a singleton set where that vector is a zero vector. Now you are taking a set only with one vector, but this vector u is a non-zero vector. So let us see whether this is how this will be linearly independent. So one vector is that, so take one scalar a and write the vector equation a into u is equal to 0. Now a into u, when can it be 0? It will be, the product au will be 0 when any one of these two, a or u, are zeros, but u is non-zero. So this is true only if a is equal to 0, since u is non-zero. So a must be 0 here. If a is non-zero, this is not true. What do you mean by that? This vector equation has only zero solution, no other solution for this. That means set containing u, a singleton vector, where this u is a non-zero vector, is always linearly independent. Now let us come for the third one. A set containing two vectors. Before this you had seen a set containing single vector. Now we are seeing if there are two vectors, then a set containing two vectors is linearly dependent when if one vector is a scalar multiple of the other. That means if you are given two vectors, just by observing, you need not work out anything. If one vector is a multiple of the other vector, then that set of two vectors is linearly dependent. You need not apply any method. Let us see how is it. So I take a set of vectors u and v, two vectors. So I have to see that this will be LD only if either u is a multiple of c, v, or v is a multiple of u, where c and d are scalars. So let us take this example. So u is equal to 1 minus 3 I have taken, v is equal to 5 minus 15 I have taken. I have taken in such a way that v is equal to 5 minus 15 is nothing but 5 into 1 minus 3, that is 5 times u. So I have taken v as 5 times u. After taking u, I have taken v as 5 times u. Then let us see what is its det value. Consider a, because how do you determine the LILD? So take a 2 by 2 matrix. This is, so take det A. Determinant of A will be 1 into minus 15 minus of 5 into minus 3, which is a minus 15 plus 15, 0. Det A is 0. When det A is 0, these two columns, whichever the vectors you have, these will be linearly dependent. Why is it linearly dependent? Because I have taken v as a multiple of u. Now let us make a little change in this. Let us see here. Let u is 1 minus 3 the same, but I'll take v as 5 and minus 10. Then can I write it as in the previous? 1 into 5 is 5, but minus 3 into 5 is not minus 10. So here v is not a multiple of u, or u is not a multiple of v. That is, then let us consider A, the matrix A again, 1 minus 3, 5 minus 10. Then what will be det A then? If you expand determinant A, it will be non-zero. That means determinant is non-zero means this set of two vectors is not LD, it is LI. So from this what can you say? If you just see two vectors in any set, if one is a multiple of the other, then they are linearly dependent. If one is not a multiple of the other, then they are linearly independent. Let us discuss some more points. First one is a set containing a zero vector is always linearly dependent. That means suppose I take three vectors u, v, w, where one vector w have taken it as a zero vector. Then what is matrix A here? How do I decide whether it is Li or LD? I'll take them in a matrix. So because there are three vectors with three rows, 3 by 3 I'll get. So I've taken these in A, 1, 2, 0, or 2 minus 2, 0, 3, 0, 0. Then what will be det A, 0, why? In any, what are the properties of determinants? If in any matrix, either entire one column or one row is 0, then that determinant of that matrix will be 0. So det A is equal to 0. Why are you getting this det A 0? Because you have taken a 0 vector in that. When det A is equal to 0, then these three vectors will be linearly dependent. That means in any set, if you have a 0 vector in that set, then that set is always linearly dependent. Next point, more than n vectors in vector space Rn are linearly dependent. So let us go through it by an example. Suppose I take three vectors 1, 2, minus 2, 3, 0, 1. Three vectors in R2. See, this is 3. This is 2 here. So this 3 is more than 2. Let us see how these are linearly dependent. Now, since it will not give me a square matrix, I will go by the second method, that is echelon form, augmented matrix AD. So 1, minus 2, 0, 0, and then 2, 3, 1, 0. Now use the transformations, because this is pivot position. You have to make this 2, 0 for R2. What you do is R2 plus minus 2 times R1. If you do that, then this is transformed to 1, minus 2, 0, 0, and then 2 minus 2 is 0, and then 3 minus minus 2 into minus 2, 4, 3 plus 4 is 7, and then next one will be 1 minus 2 into 0, so it is 1, 0. Now I got first row pivot position 1, and this is 0 here, and the second row pivot position is 7, and there is no more row. So my echelon form is completed. Now how many pivot columns? I have total 3 columns. Among those 2 are pivot columns. Only C1, C2 are pivot columns, means only x1, x2, 2 basic variables. x3 is a free variable. When there is a free variable, there will be infinitely many solutions. That means even non-zero solution exists. When non-zero solution exists, then the vectors will be linearly dependent. Why? Because in R2, you have taken 3 vectors, more than 2. So in the same way in R2, if you take 4 vectors, 5 vectors, 6 vectors, all those will be linearly dependent. So in the same way, I can say now more than 3 vectors in R3. That means in R3, if you take 4, 5, 6, 7, and so on vectors, number of vectors, they will be LD. More than 4 vectors in R4. In R4, up to 4, you can have, you may have Li or you may have LD. But if you take more than 4, that is 5 vectors, 6 vectors, 7 vectors, they will be linearly dependent. Then and so on. In general, you can say more than n vectors in Rn are always linearly dependent. Now let us quickly look at these problems. By inspection, determine whether the following are Li or LD. So without working anything, just by inspecting and keeping the previous points what we discussed, we will see whether they are Li or LD. First one, how many vectors are given? 1, 2, 3, 4. Where are these? You have only 2 rows, means these 4 vectors are in R2. But so 4 you have here 2, 4 is greater than 2. In R2 more than 2 vectors are LD. So these vectors are LD, because since 4 vectors in R2 are LD. Now let us take the second one. 2 minus 4, 8 minus 3, 6 minus 12. So here only 2 vectors are there, where in R3, so there is a chance for Li or LD, if a chance is there for both. Then let us see, but what can we observe here? Minus 3, 6 minus 12 is equal to minus 3 by 2 times of 2 minus 4, 8. So the second vector is a scalar multiple of the first vector. When it is like that, then these vectors will be linearly dependent. Let us see the next one. There are 3 vectors again given, 5 minus 3, 1, 0, 0, 0, minus 1, 2, 4. This is straight away LD. Why? Because there is a 0 vector in this. Now let me prove an important theorem on linearly dependent vectors. Its statement goes like this. An indexed set of vectors v1, v2, v3 and so on vp of 2 or more vectors, that means minimum 2 vectors should be there in this, with v1 not equal to 0. The first vector should not be 0. is linearly dependent if and only if there exists some vector vk where k is greater than 1, which is a linear combination of its preceding vectors. So here, if there is an indexed set, means you have this is first element, second element, third element, and so on, pth element like that. If there is a set of vectors which has a minimum 2 or more vectors, then where the first element v1 not equal to 0, then this set is linearly dependent when if and only if there exists some vector vk. So some vector among these, but what is the condition? K is greater than 1. That means it cannot be v1. Either it is v from v2, v3 and so on, any one of v2 to vp. It cannot be v1. So whatever this vk, k should be greater than 1 means this vk cannot be v1 other than v1. It can be any of the other vectors, which is a linear combination of its preceding vectors. So here the condition preceding, what are the preceding vectors for vk, v1, v2, v3 and vk minus 1. That is why if you take k is equal to 1, then what happens? That vector will be v1. There will not be any preceding vectors to v1. That is why this vk should be k greater than 1. It should be like other than v1 in among any other remaining vectors v2 to vp. There must exist a vector which is a linear combination of its preceding vectors. Let us prove this theorem. So its proof is like this. So we are given with let set containing v1, v2, v3 and so vp be an indexed set with the condition that v1 not equal to 0. So first element should not be 0 element. It must be non-zero element. Other elements can be, it depends. Now what do you have to prove? This theorem is if and only if theorem. That means if you take this set is linearly dependent, then you have to prove, implies you have to prove there exists some vector vk where k is greater than 1. That means from v2 to vp, which is a linear combination of its preceding vectors. So you have to take it as LD and you have to prove this condition. Conversely, the second part of the theorem is if there exists some vector vk where k greater than 1, which is a linear combination of its preceding vectors. If you get in that set any vector vk, one vector vk, which can be written as a linear combination of its preceding vectors, then implies the set is LD. So you have to consider that there is a vector with this condition and you have to prove this. Let us see how these two parts proofs will be going on. So let us come for the first part of the theorem. In the first part, we will suppose that the set of these vectors v1, v2, v3 and vp is linearly dependent. Using this, you have to find out vector vk such that it is a linear combination of its preceding vectors. So let us suppose that it is linearly dependent. If it is linearly dependent, what is the definition says? By definition, there exist scalars c1, c2, c3 and so on cp. How many vectors are there? Those many scalars. Not all zeros. All of them shouldn't be zero. A minimum one should be non-zero or more than one, or all also can be non-zero. But all should not be zeros, such that their linear combination c1 v1 plus c2 v2 plus and so on plus ck vk plus and so on plus cp vp is equal to 0. This is equation 1. So you have considered scalars and you have written the matrix, this vector equation. So how are these scalars? Not all zeros. That means some are zeros, some are non-zeros. Now let us suppose in this way, let k be the largest integer for which c1 not equal to 0, c2 not equal to 0 and so on ck not equal to 0 and ck plus 1 is 0, ck plus 2 is 0 and so on cp is equal to 0. Right, so I am choosing the scalars. So I have the choice that we can take some of them 0, some of them non-zeros. For that, what I am thinking is let k be the largest integer. That means I am putting first all the non-zero scalars, then after this all the zero scalars. That means all the scalars I am keeping in some order. K is the largest we are saying. Then k must be less than or equal to p. Why? How many vectors are there? P vectors. How many scalars will take? P scalars will take. So what is that maximum k I can up to Cp. So this k must be less than or equal to P. That means if you have suppose 5 vectors. So 5 scalars you will take. Then how many scalars maximum you can think it as non-zero? Up to 5 scalars. So you can have one non-zero scalar, you can have two non-zero scalars, you can have three non-zero scalars, you can have four non-zero scalars, you can have five non-zero scalars. But if you have only five vectors, you can't take six non-zero scalars. So if I say k is the largest integer up to where the scalar ck not equal to 0, the maximum limit for k should be is less than or equal to p. Since there are p vectors, you will choose this. So now we have chosen k, then we put the condition that k is less than or equal to p. Then what is the lower limit for k? We will prove that here k must be greater than 1. Then for that, if I want to prove this, I will suppose its contradiction. For this, let k is equal to 1. What happens if k is equal to 1? Then that means the maximum index for C is 1. Up to there it is non-zero. Afterwards all are zeros. So k is 1 means only up to C1 not equal to 0. From C2 0, C3 0 and CP 0. Is it clear? Then substituting in equation 1 we get C1 V1 plus C2 V2 plus and so on plus CK VK plus and so on CP VP is equal to 0. This we have considered equation 1. Then substitute here C1 V1 plus, then what did we suppose? What about C2? 0. So 0 into V2 plus and so on plus. Again we see what is CK. CK is also 0. 0 into VK plus and so on plus 0 into VP is equal to 0. Then which implies I will get C1 V1 is equal to 0. Which implies V1 must be 0. Why? Because you suppose that C1 not equal to 0. But this is a contradiction. Since V1 is a non-zero vector, the set is whatever the set you have taken, then it is containing all the non-zero vectors. So what is the possibility why you are getting contradiction? Because you suppose that k is equal to 1. So k is not equal to 1, that is k must be greater than 1. So we have just defined k and we have put the limits for k. Maximum limit is up to p and the minimum it should be greater than 1. Now let us consider equation 1 and 2 again. What did we write in equation 1? C1 V1 plus C2 V2 plus and so on CK VK plus and so on CP VP is 0. That is equation 1. In equation 2, what did we suppose? K is the largest integer for which C1 to CK, all these are non-zero scalars. After CK plus 1 to rest of the scalars are 0 scalars. And we proved that this k limit should be, its maximum should be less than or equal to p and minimum should be 1. That means you can have two non-zero scalars and the remaining all zero scalars, or you can have three non-zero scalars and remaining all zero scalars, or four non-zero, five non-zero, depending on how many ever you have taken p. Now let us substitute 2 equation 2 in 1. So if you substitute that, then you will get from here ck in place of ck plus 1, you will write 0. In place of ck plus 2, you will write 0 plus and so on plus. In place of cp also you will put 0. So 0 into vp is equal to 0. Which implies we have c1 v1 plus c2 v2 plus and so on. ck minus 1 vk minus 1 plus ck vk is equal to 0 till here. Then keep the ck vk this side and send this rest of the things onto the right hand side. You will get ck vk is equal to minus c1 into v1 plus minus c2 into v2 plus and so on plus minus ck minus 1 vk minus 1. Then what is vk then? Divide this RHS with ck, then you will get minus c1 by ck v1 plus minus c2 by ck v2 plus and so on minus vk minus 1 by ck vk minus 1. This I am writing it as this as d1, this as d2, this and so on plus this as dk minus 1, vk minus 1. I got one more linear combination. Vk is equal to, it's a linear combination of v1 to vk minus 1. What do you mean by that? There is a vector vk which is a linear combination of its preceding vectors v1, v2 and so on, vk minus 1. So this is what we proved the first part. So let us now prove the second part. What is the second part of this theorem? In this, I will suppose that there is some vector, there exists some vector vk for k greater than 1, that means from v2, v3 and so on, not v1, okay, which is a linear combination of its preceding vectors. Then supposing that implies I have to prove the set containing these p vectors is linearly dependent. So conversely, let us suppose that there exists a vector vk for k greater than 1, which is a linear combination of its preceding vectors. What are the preceding vectors of vk? v1, v2, v3 and so on, vk minus 1. So what do you mean by it is a linear combination of its preceding vectors? So for that you can take scalars. For some scalars c1, c2 to ck minus 1, we can write vk as a linear combination of preceding vectors, that is c1 v1 plus c2 v2 plus and so on, ck minus 1 vk minus 1. Implies bring this vk this side, it becomes minus vk is equal to 0. Now this minus vk I'll write in the next step as plus minus 1 into vk is equal to 0. Now implies for the same this thing in the previous step I will add 0. That means I'll write c1 v1 plus c2 v2 the same ck minus 1 vk minus 1 plus minus 1 into vk plus rest of the I will add some more terms, 0 into vk plus 1 plus 0 into vk plus 2 plus and so on, 0 into vp is equal to 0. Because all this whatever I added is 0, because each scalar I have taken it as 0. Now here if you observe, you have a linear combination of v1, v2, vk minus 1, vk plus 1, vk plus 2, vp. That means linear combination of all p vectors you have vector equation is equal to 0. Then what are the scalars? c1, c2, c and so on, ck minus 1, minus 1, 0, 0, 0, 0, 0. Now here among all these scalars, minus 1 is a non-zero scalar. And what are the other scalars? So if you take c1, c2 and so on, ck minus 1 and this minus 1 is here and rest of the scalars are zeros. Now among these scalars, we don't know what are c1, c2 and so on, ck minus 1. They can be zeros or non-zeros. These are all zeros, but compulsory I have one non-zero scalar minus 1. That means all these scalars are not all zeros, right? Because all these can be zeros. These are all zeros, but minus 1 is not 0. So these are all not all zeros. Then if you have like that, what do you mean by that? This set of scalars v1 to vp must be linearly dependent. Hence this theorem is proved.